Hello friends, myself Dr. Shweta Patel. Today I talk about the UV visible spectroscopy. So first of all, the principle of UV visible spectroscopy. The IR radiation region extends from 10 nanometer to 400 nanometer and the visible radiation region extend from 400 nanometer to 800 nanometer. इन शॉर्ट यहाँ पे जो यूवी रेडिएशन है उसकी जो रेंज है वो होती है 10 नैनोमीटर टू 400 नैनोमीटर एंड विजिबल रेडिएशन की जो रेंज है वो होती है 400 नैनोमीटर टू 800 नैनोमीटर. हियर near UV region it is 200 nanometer to 400 nanometer and far UV region is below 200 nanometer. Far UV spectroscopy is studied under vacuum condition. The common solvent used preparing sample to be analyzed is either ethyl alcohol or hexane. सो यहाँ पे सेकेंड बात करते हैं हम इलेक्ट्रॉन ट्रांजिशन की. यहाँ पे डिफरेंट टाइप के ट्रांजिशन शो किए हुए हैं लाइक दी सिग्मा टू सिग्मा स्टार ट्रांजिशन, देन पाई टू पाई स्टार ट्रांजिशन, एन टू पाई स्टार ट्रांजिशन and n to sigma star transition. So here the possible electronic transition are first is the sigma to sigma star transition, pi to pi star transition, n to sigma star, then the n to pi star transition, sigma to pi star transition and pi to sigma star transition. So here first sigma to sigma star transition. So in this sigma to sigma star transition, sigma electron from orbital is excited to corresponding anti-bonding orbital sigma star. The energy required is large for this transition. For example, methane has a carbon hydrogen bond only and can undergo sigma to sigma star transition and shows absorbance मैक्सिमा एट 125 नैनोमीटर. इन शॉर्ट यहाँ पे जो सिग्मा टू सिग्मा स्टार ट्रांजिशन है उसमें सेचुरेटेड हाइड्रोकार्बन्स जो होते हैं उसमें कार्बन हाइड्रोजन बॉन्डिंग होता है, उसमें अवेलेबल होता है सिग्मा टू सिग्मा स्टार ट्रांजिशन. Now second, pi to pi star transition. So in the pi to pi star transition, pi electron in a bonding orbital is excited to corresponding anti-bonding orbital pi star. So compounds containing multiple bonds like the alkenes, alkynes, carbonyl, nitriles, aromatic carbons, or the aromatic compounds etc. undergo pi to pi star transition. सो यहाँ पे जो पाई टू पाई स्टार ट्रांजिशन है उसमें जनरली डबल बॉन्ड एंड ट्रिपल बॉन्ड होता है और द कार्बोनिल ग्रुप होता है. देन alkenes जनरली एब्जॉर्ब इन द रीजन 170 to 205 nanometer. Now talk about n to sigma star transition. So in the n to sigma star transition, saturated compounds containing atoms with lone pair of electrons like oxygen, nitrogen, sulfur and halogens are capable of n to sigma star transition. These transitions usually requires less energy than sigma to sigma star transition. The number of organic functional groups with n to sigma star peaks in UV region is small, 150 to 250 nanometer. Now talk about the fourth transition. It is n to pi star transition. An electron from non-bonding orbital is promoted to anti-bonding pi star orbital. Compounds containing double bond involving heteroatoms like carbon double bond oxygen, carbon triple bond nitrogen and double bond oxygen undergo such transition. So यहाँ पे जो n to pi star transition है उसमें heteroatoms होते हैं और double bond present है. Now n to pi star transition require minimum energy and so absorbance at longer wavelength around 300 nanometer. Now I talk about n to pi star transition and pi to sigma star transition. So these electronic transition are forbidden transition and are only theoretically possible. Thus n to pi star and pi to pi star electronic transitions show absorbance in region above 200 nanometer which is accessible to UV visible spectrophotometer. The UV spectrum is of only a few broad of absorbance. So here sigma to pi star and pi to sigma star transition are only forbidden transition. Now I talk about the terms used in a UV visible spectroscopy. So here first is the chromophore. So first question is the what is the chromophore? The part of a molecule responsible for imparting color are called as a chromophore, or the functional groups containing multiple bonds capable of absorbing radiation above 200 nanometer due to N to pi star and pi to pi star transition. For example, NO2, N double bond oxygen, carbon double bond oxygen, carbon double bond nitrogen, carbon triple bond nitrogen, then carbon double bond carbon and carbon double bond sulfur, etc. So to interpret UV visible spectrum, following points should be noted. First is the non-conjugated alkenes show an intense absorbance below 200 nanometer and are therefore inaccessible to UV spectrophotometer. Then the non-conjugated carbonyl compound or the group give a weak absorbance band in the 200 to 300 nanometer region. So here some examples are chromophore. Like here first is the acetone, which has the lambda maximum value is 279 nanometer, and that cyclohexane has a lambda maximum, it is 291 nanometer. When double bonds are conjugated in a compound, lambda maximum is shifted to longer wavelength. Like here first example is the 1,5-hexadiene, has a lambda maximum value is 178 nanometer, and 2,4-hexadiene has lambda maximum are 227 nanometer. Now third point, it is a conjugation of carbon double bond carbon and carbonyl group shifts the lambda maximum of both groups to longer wavelength. Ethylene has a lambda maximum value is 171 nanometer, and acetone has the 279 nanometer lambda maximum. So here some other example like crotonaldehyde has the lambda maximum value is 290 nanometer. Now I talk about the second point, it is oxochrome. The functional groups attached to a chromophore which modified the ability of the chromophore to absorb light, altering the wavelength of or the intensity of absorbance. It is called the oxochrome. Or the functional groups with non-bonding electrons that does not absorb radiation in near UV region, but when attached to a chromophore alters the wavelength and intensity of absorbance. So these are some example of oxochrome like the benzene, phenol and aniline, and its delta value is 255 nanometer for the benzene and the 270 nanometer for the phenol and 280 nanometer for the aniline. Now I talk about the absorbance and intensity shift. So here the four shift. First is the bathochromic shift. It is also called the red shift. Second is the hypsochromic shift. It is blue shift. And third is the hyperchromic effect. Then fourth is the hypochromic effect. So now I talk about the first shift. It is a bathochromic shift and it is also called the red shift. So when absorbance maxima of a compound shifts to longer wavelength, it is known as the bathochromic shift or the red shift. The effect is due to presence of an oxochrome or by the change of solvent. For example, an oxochrome group like OH, OCS3 causes absorbance of compound at longer wavelength. Then in alkene medium, para-nitrophenol shows red shift because negatively charged oxygen delocalize more effectively than the unsaid pair of electrons. Here you can see that the reaction of this para-nitrophenol. So para-nitrophenol is react with the alkaline medium and getting the here the alkaline medium, it is abstract the hydrogen for the OH and getting the O negative. So first of all, the when the para-nitrophenol its delta value is 255 nanometer. After the reaction, it Lambda maximum is 265 nanometer. Now I talk about the second shift. It is a hypsochromic shift and also got the blue shift. When absorbance maxima of a compound shifts to shorter wavelength. In the red shift, it is the longer wavelength, and in the blue shift, it is a shorter wavelength. It is known as hypsochromic shift or the blue shift. The effect is due to presence of an group causes removal of conjugation or by the change of solvent. Here, aniline shows blue shift in acidic medium. It lose conjugation. So here you can see that the aniline is reacting with the H plus in the acidic medium and getting the NH3 plus Cl minus salt formation. And when the aniline, its delta value is 280 nanometer. But after this reaction, its delta value is 265 nanometer. So this is a blue shift. Now I talk about the hyperchromic effect. This is the third number. When absorbance intensity of a compound is increased, it is known as a hyperchromic shift. If oxochrome introduced to the compound, the intensity of absorbance increases. Pyridine, its delta value is 257 nanometer, and 2-methyl pyridine, its delta value is 260 nanometer. Now last effect, it is a hypochromic effect. When absorbance intensity of a compound is increased, it is known as hypochromic shift. Here two examples, first is the naphthalene and second is the 2-methyl naphthalene. So in the first naphthalene, its absorbance intensity is 19000, and the 2-methyl naphthalene, its absorbance intensity is 10250. So these are shifts and effects. Here the graph of this absorbance versus the wavelength. Here the first is the hyperchromic shift and down is the hypochromic shift, and blue shift and red shift. So red shift having the longer wavelength and blue shift having the shorter wavelength. In the hyperchromic shift, it is the absorbance intensity is high in the hyperchromic shift, and the absorbance intensity is low in the hypochromic shift. So now last topic, it is the application of UV visible spectroscopy. So application of this UV visible spectroscopy, first is the qualitative and quantitative analysis. So it is used for characterizing aromatic compounds and conjugated olefins. It can be used to find out molar concentration of the solute under study. Then second is the detection of impurities. It is one of the important method to detect the impurities in organic solvents. Then third is the detection of isomers are possible, and fourth is the determination of molecular weight using Beer's law. Thank you.